This video is about electronegativity and bond polarity. Electronegativity is the ability of an atom to attract toward itself the electrons of a chemical bond. So this is about how much does an atom really pull or tug electrons towards itself when it is involved in a chemical bond. Electronegativity increases going left to right on the periodic table, so going left to right across, and then from bottom to top on the periodic table. So this means the elements in the upper right-hand corner of the periodic table are going to be the most electronegative, and the elements in the lower left-hand corner of the table are going to be the least electronegative. And it doesn't really apply to the noble gases here because the noble gases really aren't involved in much chemical bonding whatsoever. They've already got a filled octet, so they don't really want to bond much, if ever. So this scale of electronegativity, it's called a Pauling scale, is from 0 to 4. So fluorine's 4 is the highest electronegativity. For example, let's consider the bond between hydrogen and fluorine. Hydrogen's electronegativity we find on this scale is 2.1, okay? And fluorine's electronegativity is 4.0. So then we take the difference between them. It's always just the larger number, the 4, minus the smaller 2.1 to get a difference of 1.9. That's considered a large electronegativity difference. And that really tells us that the more electronegative fluorine is going to really tug electrons towards itself. So they don't share these two bonding electrons very equally at all. They're really tugged over toward the fluorine. And oftentimes we draw this with a polarity arrow, showing fluorine is pulling on the bonding electrons. And the result is a really unequal sharing of electrons and what we call a polar covalent bond. So when we draw this polarity arrow, we're indicating that the HF bond is in fact really polar. Okay, so bond polarity. In general, electronegativity differences that are less than or equal to 0.4 are considered a non-polar covalent bond. Electronegativity differences that are greater than or equal to 0.5 or less than or equal to 1.9 are considered polar. So basically 0.5 and above is polar. Greater than 1.9, so like 2 and above basically is ionic. And with ionic bonds, you'll generally notice a metal with a non-metal or non-metals as well. Like the presence of that metal, will really tell you also that you have ionic bonding. It's not always present, but most of the time, the metal there will also tell you that you have an ionic bond. So what do we need to know about dipole moments then? I drew one in for you with HF. That was our first dipole moment that we were looking at. Polar covalent bonds have one end of the molecule that is slightly positive. So for us, that would be the hydrogen end of the HF. And the other is slightly negative. And so that positive end can be indicated with this little delta plus, and this little delta minus can be used to show that there's a slightly negative end, and that is called the dipole moment. So the dipole moment is just used to show polarity of our bonds and show that the bond is polar. And the way that you draw that is you're just drawing like a number 8, and then you're stopping short of kind of finishing that 8. And it's this, Greek lowercase delta that's used to really mean partial or a little bit. So the idea here is it's not a full-on +1 or -1 charge, but it's partially charged. So with HF, the hydrogen side is slightly positive, delta positive. The fluorine side that's pulling electrons towards itself is slightly negative. And we draw the polarity arrow from the positive end toward the negative end. And then, this kind of crossbar basically on the H, kind of reminds me of a plus and reminds me that that end is slightly positive. Okay, so let's practice trying to find polar and nonpolar covalent bonds. And we're going to draw a dipole moment only over the polar bonds. Nonpolar bonds don't get a dipole moment at all. So what we do is we look up the element's electronegativity. So we go back to that scale. And we go, okay, bromine is a 2.8, but another bromine is also 2.8, and so that difference is 0, and that is going to be nonpolar. Whenever you have two of the same elements in a bond, those are nonpolar and they don't get dipole moments. What about chlorine and carbon? Well, chlorine is a 3.0 and carbon is a 2.5, and so the difference is 0.5. That just makes the cut. 0.5 and above is considered polar. Now we're going to draw our arrow toward the more electronegative chlorine because it's the one tugging electrons towards it. So it ends up with the arrow towards it. You could also have done a delta minus above chlorine and a delta positive above carbon. That works too. You know, both of those are showing bond polarity. I kind of prefer the arrow because I feel like it's kind of simple, but that's just me. Okay, hydrogen's 2.1 and carbon is a 2.5. Now we always do the larger electronegativity minus the smaller electronegativity, 2.1. We don't want to end up with any negative numbers here. Electronegativity differences are always positive. This is a positive 0.4. Don't draw any polarity arrow in here because that does not make the cut. It's not 0.5 to 1.9. So it's not polar. How about oxygen to hydrogen? Oxygen's electronegativity is 3.5 minus hydrogen's is a 2.1. So that difference is 1.4. That's polar. Draw in your polarity arrow. It should be going toward the more electronegative oxygen. And we could also have done a little delta minus for O and a little delta plus for H, and those work as well. So only drawing polarity arrows in when the bond is actually polar. Okay, so how does this apply to the whole molecules that we've been talking about? Well, in order for a whole molecule to be polar, it must have asymmetrical shape, so polar bonds can't just cancel each other out. So that will happen if a central atom has a lone pair or two on it. That'll make it asymmetrical. Sometimes the central atom is bonded to more than one type of element. For example, a carbon could be bonded to some hydrogens. That would be a nonpolar bonds, but bonded to some chlorines, those would be polar, and that'll make it not symmetrical. So we're looking for something that makes it asymmetrical, like lone pairs or different atoms on the central atom. What are some common errors in assigning molecule polarity? Well, you need to draw the Lewis structure of the molecule to determine the polarity, and you need to know the difference between a polar bond and a polar molecule. So those are two big things. Now the polar bond, we tell that by electronegativity difference, right? Electronegativity. That's how we figure out our polar bonds. So you need to first, really look for polar bonds. So oxygen here in water, let's determine if water is polar. Oxygen will have two lone pairs. That will make water a polar molecule because those O to H bonds we know are polar, and they're not going to cancel out because of the bent shape. They're actually going to be additive, and the overall molecule polarity is toward the O's. If each O to H bond is polar, then there will be an overall polarity where the O end is slightly negative and the H end is slightly positive. Okay, I'm going to clean that up just so it's easier for us to see what's going on. Let's look at CO2 and decide if it is polar. So the carbon atom doesn't have any lone pairs on it, only bonded to O. It has these C to O polar bonds, but here they're symmetrical and they actually cancel. So the net result is that CO2 overall is not polar. So here's an example where one is polar, because it's asymmetrical, and one is nonpolar because, we get a canceling out, or a symmetrical, where two polar bonds actually are able to cancel each other out. So now you know how to figure out if bonds are polar and if molecules are polar.